The title of the paper is Optimal Location of Phasor Measurement Units to Enhance State Estimation of Power System. Engineer Atallah, he is the first author. He was supposed to present this paper. And Dr. Khalid Al-Awasa, of course, this work is part of his MSc dissertation. Dr. Khalid Al-Awasa, he was his supervisor, but he is currently outside Jordan. He is spending his sabbatical year in Sultan Qaboos University, and I was the co-supervisor. He graduated like 2-3 years ago, so he is not a fresh graduate. That's why maybe he forgot his own work. That's why he could not attend the conference. So in my presentation, I will come across some topic related to the content of the paper, like the PMUs, state estimation, the combination between phasor measurement units and state estimation, and other like small topics related to the content. Then at the end of the paper, I will come to the results obtained in this paper. I will start with this broad statement. Recent power system blackouts showed that operation of interconnected power system with high level on operation security and stability is not achievable with limited system knowledge. So this means secure operation of the power system can be achieved if the transmission system operators, TSOs, have reliable information of the total system state. Now, coming to the PMUs. PMUs, maybe it is common, well-known now, technology. They measure the phasor voltage, the amplitude and angle, phasor current, frequency, and drop-off, the rate of change of frequency, which is very important information for the even for the inertia studies in power system. These measured quantities, they are taken with respect to a common time source for synchronization, which is the Global Positioning System, GPS. The PMU data is very precise. It can capture the dynamic behavior of the power system to determine the exact sequence of events. This is the functional block diagram of phasor measurement unit, which include the receiving the GPS signal, then combined with the phase locked oscillator to have a timestamp to the quantities measured. Then also we have the analog signals received from the substation, from CT and VT of the substation. Then conversion from analog to digital to microprocessor, then streaming the data through the communication channels. In some references, they classify the PMUs into two categories, P class and M class. P class for the protection application, which is needs some high level requirements, and M class for the measurement. Also, it needs a high measurement accuracy. So the P class PMUs are suitable for protection and control application, since they are characterized by fast response time and low latency. This figure shows three layers. The measurement layer, where we have three PMUs, A, B, and C. So they are connected to the power system through the CT and VT. Then reporting the data with high sampling rate through any communication channel through internet. Then these data could be used for different application, and we have two kinds of application. That application that require non-real time, like the data archiving or for planning, and some application needs real-time data, like the state estimator and global trigger system. This slide shows a list of application. There is a wide scope of application for the PMUs, but here in this work, in this paper, the focus is on state estimation. Also state estimation, there are a lot of types of state estimation. We have dynamic, we have steady state. Now, when we talk about the phasor measurement unit, we have to come across the wide area monitoring system. So the use of wide area monitoring system, WAMS, enables power system dynamic behavior to be permanently monitored. WAMS provide time synchronized information. So this is the generic architecture of WAMS. We have the substation level and regional level, PDC, phasor data concentration, and super PDC, transmission level, then the real-time application. PDC has the following functionalities: acquire data from PMUs, data time synchronization, evaluates received data, send data to central PDC, exchange data with the local SCADA, archive data, perform local data analysis and protection action. Each interconnected system consists of several transmission system operator, TSOs, to observe the current state of the interconnected system. The real-time information from all TSOs is required. Hence, interconnected power system require large-scale WAMS. So we have here two kinds of WAMS, large-scale WAMS, centralized and decentralized. Now, state estimation is the process of assigning a value to unknown system variables based on the measurement obtained from the system. This is something simple. State estimator has been widely used as an indispensable tool for online monitoring, analysis, and control of power system. It is also exploited to filter redundant data, to eliminate incorrect measurement, and to produce reliable state estimates. This slide, I just want just to show through this slide the importance of state estimation. This is one of the very common, very well-known in literature blackout, 2003 Northeast blackout. The Northeast blackout of 2003 was widespread power outage through parts of northeastern and mid-eastern United States and most parts of the Canadian province of Ontario on Thursday, August 14, 2003, beginning just 10 minutes past 4, as it's clear. So what I want to mention here, that the state estimator was inactive for most of the period between, before the blackout. It was inactive for the period between 15 minutes past 12 and 34 minutes past 3 a.m. Therefore, they could not identify the system as being on the verge of collapse. So they could have avoided maybe this blackout if the state estimator was active. Now the inputs for the state estimator, simply there are two kinds of input: the network models, topology, and information about the transformer, the tap ratio, impedances, and the measurements. So this is the simple block diagram for the state estimator. Now, combining the PMUs and the state estimator, the addition of a voltage phase angle measurement by the phasor measurement units to a conventional state estimator could greatly increase the accuracy of the state estimator if implemented correctly. So PMUs enhance the state estimation of power system. To build robust state estimator, state estimation methods are modified in conformity with the integration of the PMUs data. Now we are more more close to the content of the paper. PMUs are costly and installing, still do I have 5 minutes? Okay. PMUs are costly and installing PMUs at each bus is not feasible. Therefore, the formulation of optimal placement of PMUs in power system is very important to minimize the total number while preserving the observability of the system. So this is the objective function, minimizing the cost subject to the constraint of the preserving the full observability of the system. In this paper, the IEEE 14 bus is used, and the optimal location are determined using 3 methods: depth first search, original simulating annealing, and modified simulating annealing method, and they are very common method. The author used these methods. So this is the figure shows the test case, and even in this figure also the best result also they are depicted. Here we see the result of the modified simulating annealing method shows that with 3 locations we can achieve the full observability of the system at the buses 2, 6, and 9. And this table shows the results. So modified simulating annealing method, 3 PMUs, and the buses 2, 6, 9. In his work also, without details in the paper, he applied the same methods to the Jordanian power grid, and the number of buses, 76 bus. In this slide, he's describing some information about the Jordanian power system, and I will show you the results. Here, modified simulating annealing, out of 76 buses, we can install PMUs at 26 buses, and also he identified these buses, and the system will be observable. Part of the data he used in his work is he obtained from a pilot project from PMUs already installed in the Jordanian power system at Al-Aqaba substation, Al-Gutrani substation, and these PMUs till now they are running, and these 2 PMUs they are monitoring 11 circuits. The Aqaba thermal power station, 400 kilovolt, Egypt Aqaba cable, ATPS 400 kilovolt Katrani, and ATPS 400 kilovolt Katrani line number 1, line number 2, and the Quera ATPS 132 kilovolt Aqaba Industrial منطقة صناعية. At Katrani also we have 6 monitored circuits. This is the architecture of the pilot project, Aqaba and Katrani. Also the data is transmitted from substation PMUs to enhanced phaser data concentrator at the control center at NEPCO. This is some snapshot from the system screen at the control center. This is also one of the results from the pilot project. The figure shows historical data for system frequency measured from all PMUs the first day of operation. These are some, I think this is the last slide, I think. These are some results, shows the accuracy of the methods he used, and it shows the result obtained by simulation is very close to the true data. These are the conclusion. I will not come to the conclusion, all I already embedded in my presentation. So thank you very much.